Okay, another problem involving related rates, and this one's kind of, again, another one where you really have to put in some effort to get the equation that you're going to need to take a derivative of eventually. But basically, here's the situation. They give us this boat, which is being pulled into a dock, and by the way, there's a figure in the book that's much better than mine, so you might look at that. Well, we've got a dock which is 12 feet off the surface of the water, okay, and a boat's being reeled in. It's attached to this rope, which is 13 feet long at the moment, and the rope is being pulled in at a rate of 4 feet per second. So think about this boat. It's tethered to the top of the dock, 12 feet above the surface of the water. There's 13 feet of rope out here right now, okay, but the rope's being pulled in at a rate of 4 feet per second. Now what's going to happen as that rope gets pulled in? Well, of course, there's only one thing the boat can do. It has to slide closer to the dock. Now the question they ask us in this problem is, how quickly is it moving at that moment? How quickly is it moving into the dock? Okay. So what they want is really this rate of change, the speed at which it's moving in towards the dock. Well, a couple of things here. First of all, we need some equation which relates all these numbers. And you might kind of see from the picture that the equation we need is the Pythagorean theorem. Okay? Because this is a right triangle. A squared plus b squared equals c squared. Okay, that's the Pythagorean theorem, and remember it says that the sides of a right triangle, A and B, the shorter sides, are related to the longest side, the hypotenuse, C, in this way. Okay, so no matter what length of rope is out, this is always going to be a right triangle. If it's further out or closer, it's always going to satisfy this equation. Okay, now if you think about our diagram here, this is the thing that we're calling B, right, this distance. And C is 13. Okay, now, the good news in this problem, the level of the dock is always 12 feet above the surface. So that side, the one that I've called A in my right triangle picture, that's always 12. Okay, it's not changing. Now, B and C are actually changing as this boat gets reeled in. Right, as the boat gets reeled in, the length of rope is getting shorter, and of course this distance is contracting as well. Okay, but the height is always 12, so a squared is going to be 12 squared, always. So it's 144. Okay. Now, here's the question. What is the rate of change of B with respect to t? Okay, well, where did I get that? Well, they tell us how fast C is changing. Basically, they tell us that the rope is getting pulled in 4 feet per second. What we need to figure out as a result is how quickly B is changing. Okay. So we need to compute the implicit derivative of this equation with respect to t. So we take d dt of both sides and tuck it in here. Okay, and again, the implicit derivatives here, right? T is time. So in this case, time is going to be in seconds because that's what our one measurement in time is given to us as. The derivative of 144 is 0. Okay. The derivative of b squared, well, it's going to be 2b times dB dt, right, just the generalized power rule. Okay, and that's equal to, again, implicit derivative 2c dc dt. Okay, so if you look at this equation, it's basically got things that we can substitute in now. We want to find the rate of change of b. We want to find dB dt, and we can do that if we know what b, c, and dc dt are. Okay, so what are those things? Okay, well, what's b? At this one moment in time we're looking at, what is b? Well, from the Pythagorean theorem, a squared plus b squared equals c squared. A is 12 at this moment, so we've got 144. 12 squared is 144, plus b squared, okay, is equal to c squared. Well, c squared is 169. So we can solve this for b, and it turns out b is equal to 5. Okay, subtract the 144 over to the other side and take the square root. Okay, so we're interested in computing dB dt when b is 5, c is 13, and dc dt, well, the rate of change of c, I would say, is -4, because the length of c is going to be decreasing 4 feet per second if we're reeling the rope in. So we've got numbers for everything now. Okay, dc dt, c, and b. We can plug all of those things into this equation and solve for that rate of change we're looking for. Okay, so Let's go ahead and do that here. So 2 times b, so 2 times 5, times dB dt is equal to 2 times c, 13, times dc dt. And again, I'm saying that I would probably call this -4 because c is decreasing 4 feet per second. Okay, so we can solve this for dB dt. dB dt is going to be, see, what is that, 26 times -4, it'll be -104, okay, over 10, so about -10.4, okay. And what are the units here? Well, it's a rate of change, so feet per second, okay. What that means is that the length of this side B is decreasing 10.4 feet per second at this one moment in time. And we got that just by knowing how quickly the rope's being reeled in at this point in time. Okay. So even though the rope's being pulled in at 4 feet per second, it's going to make the distance between the boat and the dock decrease much more rapidly, about -10.4 feet per second at this moment in time.